Okay, good day. Good day, everyone. Thank you very much for joining me today. My name is Phung. I am an associate professor at the Faculty of Agriculture, Yamagata University. Today, I would like to introduce Bicho Gesuido, a Japanese initiative that changed the role of a wastewater treatment plant. Let's start with a simple question. When you hear the word wastewater, do you think mainly of something that must be removed or something that may still contain value? Think about it. Instead of viewing the plant only as a final point of sanitation, we can also view it as a hub for recovering several resources, including water, nutrient, organic matter, etc. So through this lecture today, you may see how these resources can support resilient and sustainable agriculture. All right, so before discussing the resource recovery, we should remember what sewerage systems were originally designed to do. Well, as you may know, the first role is hydraulic. They collect storm water and help reduce flooding in urban areas. Okay, so this function become even more important as intense rainfall event place additional pressure on cities. Well, the second role is sanit sanitary and environmental. Sewer network collect wastewater from household and business, carry it to a treatment plant, and reduce the discharge of organic matter, suspended solid, pathogen, and other pollutant to river and coastal waters bodies. As you can see here, the photo on the right illustrate the how urban water environment can be improved when wastewater collection and treatment become effective or introduced. Uh, this is photo from Japan, especially in Tokyo, quite a long time ago. Well, these are not old function actually, and we cannot replace it nowadays. Flood protection, public health, and water quality protection remain the core responsibility of this system. The question for today is whether the same infrastructure can provide an additional public value. Well, after treatment, we still have water, we have nutrient, organic solids, and energy. Can we manage those different streams safely and usefully instead of treating them all as waste? That is a transition from a linear sanitation system to a circular resources recovery system that we will discuss today. Okay. Uh, all right. So I would like to introduce quickly about the activate sludge process. This one is a process we can separate wastewater into treated effluent and recoverable solid actually. So this is quite simple illustration, and this process is quite common to use worldwide. So please try to identify the resource that appear later in the lecture through these fingers, okay? So as you can see, wastewater first enter the primary sedimentation, the first thing over here, okay? So actually here we found some settable solid and that can be removed. The remaining water then enter the biological reactors. Here, microorganisms use dissolved and fine organic matter as food, while aeration supply oxygen required for much of that metabolism. Well, the mixture, water and microorganism was then entered a secondary clarifier, as you can see here. The biological flux settle down and the clearer treated wastewater leave the top of the tank over here. So part of the settled sludge is returned to the biological reactor through this way. Okay, and So this is basically the remaining fraction is removed as a waste. How to say? We call it waste activated sludge and sent to the sludge treatment. So basically, the treatment plant produced two main material stream, as I just mentioned. The first one is treated municipal wastewater. Okay, it's go over here. Okay, this is after the treatment is much cleaner than the influent from the beginning, but it still can contain certain things like nutrient, phosphorus, potassium, and dissolved organic matter. Okay, the second one is sewage sludge. Okay, so the sludge is the biosolid part, and this contain organic matter and nutrient also, and then it's very become concentrated. So Bichogesuido, to the project we discussed today, begin by asking how both stream can be managed as a resources without compromising the sanitation or environmental safety. Okay, then as you can see here, this is a quick look for the visual chain across the water collect from different tank I just mentioned. So as you can see from the beginning on the left-hand side of the screen, raw wastewater is turbid because it contains suspended material here. Okay, after sedimentation and biological treatment, much of that material is removed, and the final effluent become much clearer, as you can see by your own eyes over here. This visible improvement is one reason wastewater treatment has transformed urban river and coastal environment. However, uh, clear water is not the same as pure water. Treated effluent can still contain dissolved nitrogen, phosphorus, potassium, different type of salt, microorganism, and trace contaminants. Well, whether that water is suitable for discharging, for irrigation, aquaculture, or another use depend on its quality and depend on the exposure pathway. So in the scope of this lecture, we will talk mainly about how to reuse all the resources from wastewater treatment plant for agriculture, okay? And for agriculture, the remaining nutrient can be an advantage, obviously. So nitrogen can otherwise enter the river may partially replace fertilizer when the water is applied at the right rate and the right time. So at the same time, as you know, excessive nitrogen can cause also severe issue like crop blocking, nitrate loss, or nitrous oxide emission, or eutrophication. We'll discuss it further in the lecture today. So the objective is not simply to use treated effluent. It is to match the water quality, the crop payment, irrigation, management, and to form a practice or a principle that will appear repeatedly in our study in Yamagata University. Okay, so this is a quick overlook of availability of the sewerage system in Japan. So as you know, Japan has achieved a broad access to wastewater treatment, but the national average hides an important regional gap. Well, this data, as you can see, by the end of the fiscal year of 2016, well, this is the quite old data, 10 years ago. So with by that time, about 90% of the population was served by some form of wastewater treatment facility. The total, including the public sewerage, the rural community system, or on-site treatment tanks, or related system, many under different ministry, as you can see here. Again, this data is quite out of date, and I would like to encourage you to explore the latest statistics by yourself. If I remember correctly, by the end of the fiscal year 2024, this number, I mean the coverage number, has raised into about 94%. So please check it out. Okay. So what does that mean with 90 or even 94%? That means there are still people lacking access to an appropriate wastewater treatment facility. And that number is appropriately, how to say, around 5 million people. Oh, sorry, 7 million people. Okay. So this gap is essentially visible in municipal city with the few, how to say, with the population less than 5,000 residents. Okay, so this distinction matter for two reasons. Okay, the first one, conventional centralization of sewerage system become very expensive when settlement are small or dispersed. I mean, when the population is decreasing and distribution is large. Secondly, the utility that already exists in rural regions face a shrinking user base, even though the pipe, the pumps, the tanks, and treatment equipment still require maintenance. Therefore, the sustainability challenge for all this system across Japan is not only to complete the sanitation coverage to reach 100%, but it is also to make the existing infrastructure more valuable and resilient. Recovering water, nutrients, and energy cannot be solved every single financial problem, but it can create a new partnership and regional benefit around the treatment plan across the country. So I have just quickly mentioned some problem we face nowadays in the sewer system. But here I would like to emphasize it again. As previously said, Japan has already built a large amount of sewerage infrastructure. But many systems now operate in regions where population is declining and community are aging. The pipes and treatment unit do not become cheaper simply because fewer people use them. In fact, actually, the cost per se or the cost per user can increase while the fee revenue and the technical workforce decrease. This is a big problem. Okay. At the same time, extending a conventional centralized network to the remaining low density area is usually not cost effective. Though communities may need smaller decentralization of the treatment system or improve on-site treatment or carefully selected combine of the technology. I mean, there's a lot of solution for that. However, uh, so these two problem is related to question. The first thing is, how do we sustain the infrastructure that already exists? So we already have the infrastructure, we already built the treatment facility across the country. How we sustain their operation? Okay. The second question is, how do we serve the remaining population efficiently? Okay. So this is big two question. However, today I'll only talk about the one of them related to Bisoge Suido. So Bisoge Suido respond to the first question by adding the one aspect, a resource recovery role. Okay. So the treatment plant can provide reclaimed water, nutrient, soil, fertilizer, biogas, electricity, heat, carbon dioxide to nearby user or to local community. So we'll explore it in the today lecture, okay? But these benefits will not replace the core management of the utility. They can improve the use of existing facility, reduce some agriculture input like fertilizer and water, and also it can connect the cigarette utility with farmers, business, researchers, and wider community. So in other words, infrastructure sustainability become a regional system question rather than only a wastewater engineering question. Okay, so far we talk a lot about the a wastewater or water engineering thing, but I hope you can adopt this concept. All right, so why wastewater engineer like us care about fertilizer markets? Well, as you know, Japanese agriculture relied heavily on imported fertilizer raw materials. Here is the data for the fiscal year 2022 or so, several years ago. You can see that in the case of urea, so Japan was depend on overseas resources for more than on for around 95% of urea. And as you can see here, in the case of ammonia, phosphate, and potassium chloride, Japan almost depend 100% on overseas country. And in several cases, as you can see by different country name here, the imports was also concentrated in a small number of country. For example, in the case of ammonium phosphate, is totally relied on USA and mainly China. Okay, so this creates vulnerability. So as you can see, export restriction, shipping disruption, and geopolitical conflict, energy price, and exchange rate can all affect the fertilizer availability and the cost. So this urgently required an alternative fertilizer resources for domestic agriculture sustainability. So this is the big problem Japan is facing nowadays. All right, and then here we go with the Bisogesurido concept. So, so what actually a Bisogesurido is? This actually is a national effort led by Japan Ministry of Land, Infrastructure, Transportation, and Tourism, together with local partners. The name Bisogesurido is just intentionally memorable. So as you know, um, bistro is a French word associated with a small restaurant, while gesurido is the Japanese word for sewerage. So the project uh, connect the sewerage sector with food production and regional development. The concept include the three main resources, uh, including a wastewater, or how to say, treated wastewater. This can provide the both irrigation and dissolve nutrient. The second one is cigarette sludge. This can be processed into organic fertilizer and a soil amendment product. The third one, or the third pillar, is anaerobic digestion, produce biogas, while treatment and power generation can also produce heat, and in some case, carbon dioxide for greenhouse crop production. So we'll deep dive into this in the later slide. Okay, so but I would like to pause here a bit. The important word here is not simply use. I mean, how to reuse it, but it is safe and effective reuse. So each resource need characterization, treatment, and quality control, and appropriate application pathway. And of course, we need a user who actually need it. This initiative also depend on collaboration. As I mentioned earlier, cigarette system understand the treatment process, okay? But farmer, for example, in the case of agriculture, farmer understand crops and soil, and local government understand regional need and regional circumstance. And university, like our university, can evaluate the performance and risks associated with all such kind of activities. So Visual Gesuido is therefore better understood as a partnership model and a system concept rather than one single technology. Okay, so please keep that in mind. All right. So I would like to show you the map of the Bishogetsudo practice across Japan. So as you can see here, the project or the practice of Bishogetsudo is not limited to one city or one type of agriculture product. Across the country, local governments and producers have tested the reclaimed water, derived fertilizer, and energy or carbon dioxide from wastewater treatment. Okay, so the crop and business models vary across the country because the availability of resources, climate, soil, markets, and distance between the treatment plant and the farming soil or farming land are different in different regions. Okay, so actually, the I don't recognize. I cannot read the small letter here, and also I would like you not to read it every single label. I only would like you to notice the diversity. Okay, so one location may have nearby parties or abandoned wastewater treatment facility. Another may have a strong compost market, or how to say, some area with colder climate like Hokkaido may benefit mostly from recovery heat for protected horticulture. So this is why copying a technology is not enough. A successful project begins with matching a local resources with a local demand. So this is the overall picture of Japan. Now I would like to move from this national overview to one detailed case in Tsuruka City in Yamagata Prefecture. Okay. So as you can see here, the model of Bishoke Suido in Tsuruka City combines several pathways at the same wastewater treatment plant. As you can see from the diagram here, I would like you to try to identify where water, nutrient, energy, and other product move. You may also notice that some pathways are already commercial or operational, while others remain in the research and demonstration stage. Okay, so let's take a look clearly here. This diagram is our roadmap for the rest of the lecture, okay? So I would like to stay here for a while. At the center is wastewater treatment plant. As you can see here, I think some of you already visit this wastewater treatment plant. Uh, if you have not visited this, you can actually. It's not so far from our university. So here's the center, okay? And surrounding here are four resource loop or four resource circle that I want to emphasize in today's class. Okay, the first loop is treated municipal wastewater. Okay, this one. After after the treatment in wastewater treatment plant, instead of discharging all of it directly to a river, a portion can be supplied to rice field, horticulture, or other experimental system. The water provide irrigation, as I mentioned earlier, while also dissolve nutrient like nitrogen and other nutrient may support plant growth. Okay, so in our experiment, we already use these resources for corn, forest, and vegetable. The second loop is actually I want to mention the second one begin with the sewage sludge over here. Okay, so after digestion, dewatering and composting, the biosolid can be used as a soil amendment or fertilizer for feed crops such as then corn or forest rice. So Joe crop can be useful for supporting local livestock production. We'll talk about it later also. Okay, so the third circle is energy. Okay, as you can see from this right-hand side of the screen. Okay, so anaerobic digestion produce biogas. Okay, over here. So the gas is used for electricity generation and part of the engine heat remain, how to say, the digester, how to say, remain the heating source for the digester temperature. Additional recover heat can support greenhouse production during Churuka cold winter over here. Okay, so the fourth loop is aquaculture. Okay, come back over here. Okay, so we have the current project cultivating AU fish using treated wastewater to cultivate algae, which are then incorporated into feed, while the fish themselves are cultivated with that kind of food. All right, so that is over very quick overlook of this model. Okay, so we will begin with the first resources or the most abundant one, wastewater. All right, so as you may know, even after the activated sludge treatment process here, treated municipal wastewater still contain a significant amount of nutrient. In our study in Churuca City, wastewater contain around 30 milligram per liter of nitrogen and around half a milligram per liter for phosphorus, very small amount, but then potassium also significant amount also. So please understand that these are representative value for this system, especially in Churuca, and not fixed value for every treatment plant. And wastewater quality change, as you know, with the influence seasons and treatment operation. Okay, but anyway, when treated municipal wastewater here is supplied to a rice field, for example, water and nutrient arrive together. So we supply treated municipal wastewater for a rice paddy. Okay, what go with the wastewater is water itself, of course, and nutrient. All this NPK, nitrogen, phosphorus, potassium also come to the field. Okay, and then by doing so, we can reduce the freshwater withdrawal from nature. And then also we can replace part or all the mineral fertilizer, especially nitrogen. Okay, so to figure out how it works, we have developed treated municipal wastewater fertigation research project step by step. Well, we began at urban scale over here in the left-hand side of the screen. As you can see, this model we will start, actually, we have started this model like almost, how to say, more than 10 years ago. So here we supply water and nutrient loading to the wastewater irrigation. And here we can control it closely. And then we then move to the pilot scale experiment here in the middle of the slide, and you can see. And finally, we go to the real field demonstration. And then, as you can see here, this is the wastewater treatment plant, okay, at the bottom of the photo. And then we select some field nearby for demonstration purpose. So that progression is, how to say, as you can see here, like it takes time to move from bench scale to pilot scale and to go to the field demonstration or field application. However, that progression is very important because a system that works in a pot or a small plot may have behaved differently when the flow path, weather, and soil properties or all farm operation become realistic. So in the field comparison, so here on the right-hand side, the wastewater fertigated, or we call test field, this one. They receive a wastewater from the sewage treatment plant here, and then the water is continuously flow over the field and go downside in the opposite side of the field. And then in this field, we don't use any chemical fertilizer. Okay, and then we compare the performance of this test field with the field we call control field here, where we follow the normal conventional management using chemical fertilizer and canal water for irrigation. So as seen in this graph, you can see that both brown rice yield or grain yield and then grain quality in terms of protein level, okay, um, is quite clear difference between the two fields. So we can find that rice yield and grain protein are clearly higher under the wastewater irrigation than though under the conventional field. So you may question, oh, why? Why we don't apply chemical fertilizer in the test field, but then we still get a better performance in terms of rice yield and rice protein content. So this was most likely actually because of the concentration of nutrient in the wastewater, as we mentioned previously. So treated municipal wastewater continuously supply nutrient, especially nitrogen in this case, throughout the growing season. And then that nitrogen or in the wastewater can support the plant growth and maintaining the nutrient uptake into the grain across the entire season. Okay, so the good thing here is that not only we don't use the chemical fertilizer and also waste canal water for the test field, but also the benefit is relied on economic side. So the economic implication is promising because mineral fertilizer uh, accounts for around 50% of total cost for the production. So now, as you can see, we remove it. We don't use any chemical fertilizer while we still have a good result. Okay, what does that mean? That means we can save the cost of fertilizer in this cultivation. That's pretty good, right? All right, so another benefits of this system, I mean, wastewater fertigation system is that water can be uh, clarified further. So the paddy field not how to say the paddy field is not only the farming land anymore to produce rice. It's also change the quality of the water passing through the system. Okay, so as you can see here in this finger, the blue line, so the total nitrogen concentration in the wastewater that we use to supply into the field. Okay, and depend on different date of sampling, the concentration was around more than 20 to even 45 milligram per liter over here. Okay. Down here, you can see the orange line, so the water level, how to say, the total concentration of nitrogen in the effluent. So the water leaving the rice paddy field. And you can see here, nitrogen concentration was generally much, much lower. Okay, so what does that mean here? So uh, the reduction of nitrogen concentration comparing between the input water and effluent water from the field is that rice plant take up nitrogen and store it in plant biomass and grain. In addition, soil microorganisms also immobilize nitrogen, transform, for example, ammonium to nitrate, and under sustainable condition, it even can reduce nitrates to the gaseous form of nitrogen. Okay, and then this one is very positive and beneficial for us because this concentration difference is strong evidence of a field policing effect in which a productive agriculture field or rice paddy field in this case can produce an additional nutrient removal function before the water can reach the receiving environment. So this is very beneficial, benefits because it can reduce the risk and consequence of eutrophication in the receiving water body. So I put the photo here for eutrophication, and you can see the color here. Or this is one example of the contamination or eutrophication in the receiving water. And then by reducing nitrogen concentration in the input water like that, we can avoid this kind of phenomena in our water body. All right. Then we want to see the system or the fertigation practice in another aspect. And in this case, we want to evaluate the climate performance. So we use the closed static chamber method to monitor the greenhouse gas emission, particularly methane and nitrous oxide emission from rice paddy field under the wastewater fertigation system. So this photo is illustration of the how the chamber method to work. And actually here is our student working on the gas sampling in a glass house based on the how to say the band scale experiment. So basically the chamber is placed over the rice and the water surface. Okay, then we creating a known head space over here. And then after chamber is closed, the gas sample was collected at several time points. And and if methane and nitrous oxide is being emitted, its concentration increase inside the chamber. Okay. And the rate of that increasement together with the chamber volume, area, temperature, and pressure is used to calculate the gas emission or gas fluxes. Okay, so and based on that method, we have developed an irrigation practice that we can reduce greenhouse gas emission. Actually, we call it continuous subs irrigation with wastewater. Okay, and today I don't have time to talk in detail about this irrigation method, but basically we have developed the good method that can we can by that we can reduce the emission of methane and nitrous oxide compared with the conventional uh, fuel. So as you can see here, under the optimized system, the seasonal methane emission was reduced approximately 80%. It's a tremendously reduction. And also in the good condition or in some what we call optimized scenario, we can also reduce nitrous oxide by 66% relative to the control or the conventional cultivation. So this result demonstrated a useful system lesson. So this is important, okay? So resources recovery must be designed around demand, and too much reclaimed water can mean too much nitrogen. So sometimes we supply the system, the rice system with a lot of water, a lot of wastewater. It's good, right? The nitrogen there is free, so we can supply a lot. But then climate benefits for methane can be partially offset by nitrous oxide emission when the nitrogen is was input too much through the irrigation. Therefore, how to say, this is just a quick information for you if you are interested in this technique. So irrigation scheduling, drainage, crop uptake, and nutrient loading must be all managed together. So if you are interested in this topic, please let me know, or you can contact me at the later time. Okay. Well, now I would like to move to another aspect. So as you can see from, sorry, let's I come back for several slides. As you can see here, we said that the rice cultivation from our test field using wastewater have high value of protein content. Okay, significantly higher than the normal field of the farmer. Okay, then where does the value of this come? The value of protein-rich forage rice is not only on its yield. It may also replace part of imported feed ingredient. Feed for livestock farming. And in this case, we try to, we have conducted a trial in which pig received either a conventional feed or a test feed that use protein-rich rice from our field. So, by the way, we compare the normal or general feeding, including corn and bean cake, for one pig. And on another side, we use a test pig and feed them with the substituting corn with the rice with high protein content that is grain or harvested from our field using wastewater. Okay, then for that one actually, when we use the protein-rich rice to replace some part of the corn, this one is allowed for around 56% of reduction in more expensive soybean meal. Okay, and then of course this is saving the cost for production or for livestock farming, in this case, a pig. However, more importantly, we would like to focus on the quality of the product from this test, from the pig farming. Okay, so let's talk about the carcass. As you can see here, the carcass ear increased from a 64% to almost 66%, and the proportion of grade A carcasses also appear higher in the test group, as you can see here. Okay, so if you are using the price assumption in the trial, the test feed reduced the feed cost by approximately like almost 600 Japanese yen per pig, and increase the sale value by almost 2,000 Japanese yen per pig. So this is big improvement in terms of revenue for farmer. So this trial demonstrated an important circular economy principle. Nutrients recovered through wastewater fertigation can create value beyond the crop field when the resulting feed a real livestock production need. So what I mean is by that is this. We already mentioned that we have the high yield and good protein content of the rice, right? That is direct benefit when we apply wastewater fertigation in rice field. But also, because the rice have a good quality or high protein content, we can replace the expensive corn and bean cake with rice, protein-rich rice in this case, so that we reduce the cost of livestock farming also. Okay, so that's it for that. And now let's summarize the wastewater irrigation pathway. Okay, so we have already mentioned a number of positive results. Okay, and I would like to summarize it here again. So please try to remember and recall what we had just mentioned. First, it can substitute both irrigation water, and maybe it can reduce or 100% or completely remove the need for fertilizer. Okay, so that's the first benefit. Secondly, the rice field over here can act as the nitrogen removal unit. It can lower nitrogen concentration before the water is returned to the environment. So this lower nutrient, this chat benefit is very good for the cleaning or maintaining the sustainable water environment. The third point is the system can produce high protein forage rice that can support local livestock production. And I just mentioned earlier, protein-rich rice can replace expensive soybean cake. And then by that, it can sustain the local livestock production. Okay. And the fourth positive result or the aspect is go with the climate impact. So with an with an accurate or optimized design irrigation and drainage regime, we can reduce methane and nitrous oxide emission from the rice field. Okay, so overall, this outcome connects several sustainability goals, as you can see from this slide, including food production, clean water, responsible resource use, climate action, and regional economic activities. So you may forget some information or detail, but I would like to reinforce one message. Treated municipal wastewater fertigation can generate multiple benefits when water supply, nutrient demand, and fuel hydrology and local value how to say, chains are designed together. So this is the overall picture of the benefit we may withdraw from the wastewater reuse pathway.